Okay, this is the next in a series of recordings of the improved phase activities of the Anodize team. So previously we talked about designing an experiment. We showed the experiment that they ran. We showed how to analyze the results of the experiment. And we showed how to optimize the settings of the input factors to get the most desirable responses, i.e. to get all of the responses simultaneously to hit at or near the target. And where we left off in the jump profiler, we actually showed the results and the predicted responses. All of these would put us actually at the settings of the CTQs that should give us acceptable parts. One thing one has to keep in mind is that these are ideal settings. There's no guarantee in actual practice that they'll actually hold these settings very tightly. One would hope they would, but quite often there is actually variation that occurs. And this is typically because there's not adequate control over the process factors. And when we get into the control phase of the DMAIC cycle, one of the things we have to do is come up with control plans. That is, what's the strategy to control the important inputs or factors in the process. So what do we do next? Well, it turns out JUMP has some really nice tools to help us evaluate or predict the future capability of this process if we run at these settings. Prior to this discussion, I suggest you do read the Chapter 6 Part 4 notes through page 40, and they'll walk you through basically some of the steps that I'm going through. In JUMP, if you go, again, I'll leave the profiler open, and in the Prediction Profiler menu, there is something called the simulator, and this is a way of simulating variation in the process. Notice that when I open it up, it shows you the input factors, and it says either random or fixed. Fixed means that there's no variation. So notice Anodize time is fixed at 40 minutes. It turns out that this was actually kind of interesting. The operator lowers the parts into the anodized tank, starts the anodizing process, and then sets a little simple device like an egg timer type device to whatever the specified time is, say 40 minutes. When the thing dings, the operator pulls the parts out. So the one variable that is tightly controlled in this process is time. So we say it's fixed. Random means that we do observe variation in that response in the process. So notice the setting is random. Okay, so typically we're only going to talk about they're either fixed or they're random. And I showed you earlier that we had stored standard deviations as a column property for each of the input variables except anodized time. JUMP picks up that property and says, oh, this could be a random effect in the process. Well, what happens is, assuming these standard deviations for the random effects, and let's assume the variation in these process inputs is normally distributed. Fairly common assumption for errors in process control. They often are normally distributed. So what we're going to do is run a simulation. Okay? So notice there's a little button that says simulate, and it's going to do 5,000 simulated observations, okay, for the CTQs, and we're going to see a measure of capability. So I'm going to click on simulate, and what it did, it simulated variation in the responses, okay, due to the failure to control the input variables. And then it gives you a little table where it shows you the defect rates In fact, if you right click in the middle of the table, one of the columns you can get is part per million. Okay, so notice the only major issue we have is L star. And if we look carefully, let's look at L star. L star is strongly influenced by temperature, okay, and acid concentration. And in fact, in the actual process, these are not tightly controlled. In point of fact, some of the engineers working on this project were convinced that anodized temperature wasn't all that important, and they made no effort to really control it, so it changed during the day. In talking with a chemical engineering professor at UNH who knows a lot about anodizing, he thought that was hilarious and said, well, those engineers clearly know nothing about anodizing. And now I understand what he was saying. They really weren't subject matter experts. They just thought they were. Well, it turns out that anodizing temperature is very important. In fact, notice these what we call desirability contours. They tell you how undesirable the response can become if it varies much. And you can see it's fairly sharply peaked, so we need to hold that temperature very tightly. Now we can go forward and actually do some capability analysis. And one way to do that, okay, is to take the results, okay, and simulate them to a table. Let me slide my bar over. So I'm going to make a table, and in this table you see the simulated responses, and what we can do is we can do some capability analysis. So in process capability, I talked about the tool in JUMP called Process Capability Analysis. In the Analyze menu, Quality and Process, Process Capability. And what I'm going to do is put my 4 formulas in. And by the way, these 4 formula columns contain the simulated responses. Click OK. And by the way, all of the specifications are brought over from the original table. And notice that if I go to a CPK of, let's pick one here, about 1.5, a little less. But let's say right around 1.3, somewhere in that range, that 3 of the responses actually look capable, 1 does not. Okay, and that's L star. L star is not capable. The other 3 basically are. And so if we want, we can get a CPK table. Okay, so we get a summary of reports. So basically, if we look at the CPK values, okay, you can see the only one that really is incapable is L star. Okay, so using the simulator, it allowed us to predict what our future capability will look like. So what did the team do at this point? Well, basically, as it turns out, since there was no explicit temperature control on the anodized bath, they investigated and they were able to find an affordable temperature controller that could be used with a sulfuric acid bath. Okay. So using the analysis I've just shown you, they went to management and they got an approval to install the temperature controller, and that reduced the variation substantially. So we can illustrate the idea. Let's suppose we cut the variation in half. I can simulate that by just changing the standard deviation to 0.75. By the way, they also were able to reduce variation in acid concentration, dye pH, and dye concentration by putting controls in place to make sure these variables were checked regularly and were adjusted whenever they were moving away from their targets. Okay, so let's resimulate. Okay, and see what happens. Now notice, once we resimulate, we have the variation, or we're actually now in a reasonable state of control for L star. And why L star is important: if parts have too low an L star, that indicates they're going to have a smutty surface, meaning there's actually too much dye that's been absorbed into the parts. If L star is too high, that indicates, I had that the opposite. If it's got a large number, it means it's too dark. If it has a low number, it's too light. Okay. So what this tells us is, by putting this controller in place, putting a few controls on some of the other variables, we now have a very capable process. So the simulator is a really powerful tool to use along with the optimization of your experimental results to give you some idea of what will happen in a process if you don't tightly control the inputs. So Six Sigma teams can do a great job of doing root cause analysis, implementing an improvement, but if they don't have sufficient controls in place, then the end result is they may not achieve the desired results. Okay, so this has been a short video explaining the use of the simulator and how we can use it to assess future capability, and how we can actually use it to spot areas where we may need to improve process control.